In this sketch, we're going to cover the hemodynamic principles that regulate cardiovascular blood flow: velocity, flow, pressure, and resistance. So, where better to set our dynamic scene than the flowing river delta? Adventure awaits. And here comes a boat speeding down the river, which brings us to the first concept we'll cover: blood flow velocity. Now, velocity and flow are not the same thing. When you think of velocity, think about the distance a moving object travels over time, like this speedboat traveling, about 70 miles per hour. But in the case of circulating blood, that's anywhere from 5 to 20 centimeters per second. Flow, represented by this flowing waterfall, refers to the volume or amount of blood traveling over time. Blood flow through a given blood vessel is measured in milliliters per second, but total cardiovascular blood flow of a resting adult is measured in liters per minute, about 5 liters per minute for most people. It's important to remember that flow is constant, so that the volume getting pumped out of the heart is the same as the volume coming back into the heart. To remind you of this important principle, take a look at this outflowing waterfall. It's circulating the same volume of water as its inflowing counterpart. In contrast, the velocity of flowing blood is variable depending on the cross-sectional area it's flowing through. Cross-sectional area refers to the amount of space the blood vessel occupies in 2 dimensions, often expressed as pi r squared. To help you connect these 2 parameters, we have a fast speedboat and a slow canoe, and 2 tunnels of differing size, narrow and wide. It's no accident that we've made the faster boat speeding through the narrow tunnel and the slower canoe gently moving through the wide tunnel. And the reason for this is cleverly spelled out for you here. V equals Q over A. In other words, blood flow velocity is directly proportional to blood flow and indirectly proportional to cross-sectional area. Given that flow is constant, this inverse relationship between velocity and cross-sectional area means that blood speeds through blood vessels of lower cross-sectional area and slows down at areas of higher cross-sectional area. Simple enough, right? Well, there is a catch. When it comes to cross-sectional area, we don't just mean the area of a single blood vessel, but rather the total amount of space taken up by a group of blood vessels. Let's apply a physiological example. The aorta is a pretty wide artery, right? And a capillary is super tiny. But in terms of total cross-sectional area, the capillaries, symbolized by this impressive spread of red roots, actually represent the highest total cross-sectional area. Knowing that V equals Q over A, the capillaries must have the lowest blood flow velocity, hence why the speedboat here is slowly waiting by the mangrove roots. The lower velocity of blood flowing through the capillaries makes them the ideal place for exchange of fluid and nutrients. Incidentally, these mangroves are the perfect place to offload and trade goods. Delightful. And now that we know all about velocity, let's dive deeper into the dynamics of blood flow. Blood flow is connected to pressure and vascular resistance, expressed by the equation Q equals delta P over R. In other words, blood flow will increase with a greater pressure difference and decrease with more resistance. To help you extra connect these parameters, we've added Sketchy's own Delta Princess to the mix, with its patent-pending Q-shaped paddle. Hop on as we flow through the rest of the sketch. Just watch out for that damn. Delta P, or pressure gradient, is generated by pumping of the heart. As a general rule, pressure moves from high pressure, i.e. the heart, to low pressure, i.e. the periphery. Resistance in blood vessels impedes the flow of blood. In the cardiovascular system, arterioles actually provide the most vascular resistance in the systemic circulation, much like the hole in this R-shaped dam dictates how much flow comes out the other side of the river. This means that changing arteriolar resistance will change cardiovascular blood flow. But that's all we'll say about vascular resistance for now. Check out the lesson on resistance and its impact on normal hemodynamics for a deep dive. And that's all for blood flow basics. We've covered a lot, but remember, cardiovascular blood flow comes down to two things: blood flow velocity and flow. Remember, velocity and flow are not the same thing. The determinants of blood flow velocity are flow and cross-sectional area, and the determinants of flow are delta P and resistance. I don't know about you, but we're going to take the path of least resistance over to the next sketch. See you there.